the recording actually. So it's my pleasure to introduce Eric Sir, who's a member of the technical staff at the Computer Science Research Institute at Sandia National Laboratories. And his talk today is entitled A Layer Parallel Algorithm for Training Recurrent Neural Networks. Or, well, actually, layer parallel training, nested iterations. Take it away, Eric.
Yes, thank you. Yeah, unfortunately, we didn't make quite as much progress as we were hoping on the recurrent neural network piece, although that work is still underway. So I've kind of focused on some joint work with, again, Stephanie and Jacob Schroeder, primarily, but also Lars and Nico for some of the background material. This work is really focusing on how we start up kind of this layer parallel training. I'll spend a lot of time talking about what's happening from a, just kind of giving some of the background. So you'll hear some of the repetition of Stephanie's talk. So if you're watching this in the future, you might go back and look at Stephanie's talk as well. Prior to mine, that might help kind of clear up some of the issues. Or let's see. All right. So to get into this, the first thing is what is a neural network? So we have in a neural network, we would have inputs and we would pass it from layer to layer to layer. A single ResNet layer then would take an activation, apply it to some affine transformation, add the skip connection that Stephanie motivated previously, and then get the new layer. So this would be XK, this would be XK plus 1. We can also use these ODE networks where we take, instead, we note that this looks a lot like a forward Euler kind of evolution. And so we're going to treat this as a time derivative and again use the affine transformation. But now your parameter, your weights and your biases are time dependent as well as your solution. And then the last piece is the idea of training a neural network is to determine the kind of ideal weights and biases to actually reconstruct whatever your training data requires in a yeah. So just to kind of give one slide intro on training the neural network, the idea is that we have these multiple layers, and we have to compute the gradient of this objective function. So writing this in the kind of constrained optimization, we have a loss function here, which is a function of the output of the final layer that produces the prediction. And then the constraint is, of course, the neural network evolution. And so you end up having to compute the gradient of this loss function with respect to the weights and biases, incorporating this constraint. And so you do this using forward back propagation, or if you'd rather, a forward evolution and then an adjoint solve. And so the idea is pretty simple. You do the forward evolution to compute the solution, the forward prediction that you get. And then from there, you can compute the derivative using the back propagation algorithm. And what happens is you actually transfer information from the forward solution back to the back propagation as you're computing that derivative. And this is where the kind of challenge becomes, because you can think about, well, okay, there's a number of different issues. You have this forward evolution, which serializes. So that's why this slow moving from left to right. And then the back propagation also serializes. But the added twist is that you need the information from the forward evolution to be stored and passed to the back propagation. So in fact, these systems are, you can view them as somewhat coupled. A traditional gradient descent algorithm isn't as strongly coupled as a second order Newton solve, but you can certainly view them as talking to each other. So it's not like the forward and back propagation are unrelated to each other. All right, so Stephanie talked about this work where we're trying to accelerate training with layer parallel computation. there's been a lot of advances in training neural networks that have led to substantial improvements and really kind of enabled this. The question is, how can we use parallel computing in general and HPC to really help? And so the goal, as Stephanie kind of talked about, is to develop a new dimension of parallelism to try to exploit. So these are some of the plots that we saw, these images, these parallelization strategies. We have data parallel. If you are a PDE person and you do uncertainty quantification, this looks kind of like evaluating the PDE at a bunch of different black box points and doing doing the forward evolution of the PDE. Similarly, you would be able to evaluate the neural network at a bunch of individual data samples and do the forward evolution. So you could also compute the relevant gradient as well using a backpropagation. So in this way, you're able to distribute the data across all kinds of processors and get parallelism. The problem with this is that for stochastic gradient descent, the performance can degrade as your batch size gets too large. And so that can cause an issue from the numerics perspective. And so you can only really get limited parallelism out of this approach. So then we move to the model parallelism, where we break up each layer across a sequence of processors. And this is a good idea. If you have, say, a large image or maybe a 3D kind of voxel kind of image, you might break it up across different processors just so you can process each component of the image in a coupled way. But if you need more depth to your neural network, as you add a new layer, your cost just grows with the total number of layers because it serializes. So our approach then is to provide a parallelization strategy that will allow us to decompose this network across layers. So this is kind of the picture that we have. And so you would have, say, you would put layers 1 and 2 on processor 0, layers 3 and 4 on processor 1, so forth and so on. And that would be kind of a domain decomposition kind of idea of breaking up the solution. So I have a postdoc who is kind of a traditional computer scientist. And he went to supercomputing and he said, I'm working on layer parallel ideas. And they were very concerned for him. And it was because basically it really doesn't make a whole lot of sense, right? So if you just think about it this way, you need information from the first set of layers to be passed to the next layer and then the next layer. And so it serializes. There's not really any parallelism to be had. And so I was upset about this. I didn't want my postdoc to have a bad experience. And so I ended up thinking about this a little bit and thinking about the backpropagation algorithm and the gradient descent algorithm. What happens? Well, traditionally we would do loop over the total number of iterations, would do a forward propagation to compute the kind of predicted value. We do the back propagation to compute the gradient, and then we would update our weights and biases using kind of whatever learning rate we have in the gradient. And what this assumes then, traditionally, is that these forward propagation, backward propagations are exact. But what we can do if we allow ourselves to make an error in the forward and the back propagation, that error exposes some freedom. So if we allow ourselves to make this error, we can now trade that error for greater parallelism. And so that's what we're going to do. We're going to relax the need for data dependence in the forward propagation from left to right. We're going to relax that need and allow a little error in between each layer that crosses processor boundaries, and take advantage of that to generate a scalable multigrid method. And so that's really the key thing, is to recognize that exactness, while really it makes sense, it's very, very useful, you can also relax it and get better performance out of it. And so that's really the approach that's taken to layer parallel. Stephanie alluded to this in her use of an inexact gradient computation earlier. So what are we going to do? Well, Stephanie explained this very well in multiple slides. I'm going to do it really quickly in one slide. So the idea is we have a fine level multigrid and time fine level residual network, ODE network. And what we're going to do is we're going to first relax on the fine level. So we're going to basically do the forward propagation over just your processor local set of layers. Then we're going to transfer that information, that error that you've now accumulated, but in particular between the different layers across processor boundaries, we're going to transfer it to a coarse level where we're going to solve in a fully coupled way for a course correction. Okay, so what we've done is we've introduced some error at the fine level. We've said, okay, well, now we need to fix it. So we're going to transfer it to the coarse level and accelerate the fixing of it by solving a global course correction. Then we can transfer that course correction to fine, and now we basically have less error in between the layers. And then we can relax on the fine level, again, to clean up any mistakes that we might have made locally once we did this course correction. Now we can repeat this algorithm multiple times, and it ends up converging very quickly. The key is, of course, that you use the course level to communicate from one end of the domain to the other. You can't get away with only communicating locally. That will lead to an algorithm that doesn't scale independent of the number of processors. One final point here, if you were to have kind of more layers, you can recurse this algorithm. So this is just a two-level method, but if you wanted to, you could treat this in a layer parallel fashion, then go to a third level and solve a full coarse grid correction there. So some details of the algorithm that we've kind of developed, and this is just, again, a repeat of what Stephanie has done. We use ODE neural networks, so time is equal to layers. So that leads to some questions for me, particularly about what's the actual regularity required when we get this. So if we were to drop this delta t and go back to the ResNet, would this multigrid algorithm work? And that's a question that we're still working through. The smoothing relaxation scheme is this fine, coarse, fine relaxation, where we relax on fine points, relax on the coarse points, relax on fine points again. That has the effect of doing kind of forward propagation from this red dot to the other one, adjusting on the coarse level, and then doing some more fine propagation again. And then we're using this one-shot optimization approach, although I'll show some other results that are kind of more targeting a more standard stochastic gradient descent algorithm in a few slides. So all of that is basically kind of a review of what Stephanie had talked about. So what about starting guesses? So this was alluded to a little bit earlier. In serial training, you have different weights. You have to choose the initial weights. You have many different ways to do that. There's this Clorot thing, this He, which is standard. These are both implemented to both PyTorch and TensorFlow. I would be remiss not to mention our box initialization method that we recently developed, which is in some sense a extended view of the He initialization. And then the features, the nice thing about serial training is you don't have to initialize the features. It's naturally done. because you're exactly solving the forward propagation, you don't have to guess at what the initial solution is at layer 7, for instance. However, in layer parallel, we have to again guess the weights. We could do it in the same way in serial. There might be something better. I'm not going to talk too much about this. And then the features, well, these are a bit more tricky because now we're doing an inexact propagation at the start of the algorithm. What happens? What do you guess for the input to layer 5? And so I believe in the layer parallel, the original work, we kind of just guessed 0, and we would have let it evolve from there. However, that seems a little bit, we might be able to do better if we had a better guess. And so how do we generate that better guess? Well, using kind of this idea, we're going to focus on a nested iteration kind of multigrid idea. And this is motivated heavily by this cascadic multigrid ideas from Lars and Haber. And so in this case, what we're going to do is we're going to do like a full multigrid kind of setup where we're going to start on the coarsest level, solve the neural network training problem, and then interpolate to a finer level. Again, return to the coarse level using a layer parallel algorithm for that training. And then that will give us a good initial guess. When we solve this, we're going to get a good initial guess from basically a lower resolution serial neural network. And so we're going to just then kind of repeat this process till we get to the fine level that we want. Okay. And so what's going to happen is that early time is going to be a very coarse network. And then as we kind of evolve our solution, we're going to refine it and hopefully get a better solution. So in this way, this gives us a better initial guess for both the features of the neural network, but also the weights and the biases. Okay, just to kind of reiterate what the algorithm is going to do, we're going to kind of initialize on the coarse level. In this case, we're going to just use some random weights. We're going to use the features we're going to run those serial, so no initialization is really necessary. And then for each level, we're going to do m to the raised to the L optimization iterations with a layer parallel iteration kernel. Okay, so we're going to solve kind of the gradient descent algorithm using just for each level, and then build on that neural network with an interpolation to get to the next finer level neural network. Okay. So we're going to again use this peaks data set that Stephanie talked about, and the Indian Pines image segmentation data set. So in peaks, you're classifying particle locations into these level sets. And in Indian Pines, you're going to classify corn, or what is this field composed of? Is it corn or soy or whatever? A few comments on the code. These training results are based on hand-rolled neural networks. The code itself is built on the XBraid library. It is definitely not optimized. I unfortunately wrote the hand-coded convolutions, and so those aren't the best, although we're not really using convolutions for any of these results. And then in general, the neural network architecture is not optimized. We're just using kind of simple applications of the ODE networks to focus on the parallel training process. All right, so to read these plots, I've shown two images. On the left is the peaks example with the validation or testing accuracy. On the right is the Indian Pines example. And what we have on the horizontal axis is work units. So this is the kind of the relative cost to one iteration of the serial algorithm, of the layer parallel algorithm run on just the fine level. Okay, so this red line is layer parallel. using the non-nested methodology. And these colored lines are different levels of the nested algorithm. So the blue line here is the level 0, the coarsest level neural network training. The orange line is the middle, and the green is the fine. And so what we can see is that this separation that you get between the layer parallel algorithm and the nested algorithm is a performance boost that comes from using this nested iteration strategy. And so this work units is really scaled in terms of relative time. And so you're seeing that the non-nested is quite a bit more expensive if you look across this. So for instance, from like 150 down to 25 to get to the same accuracy. Of course, that's not using the full power of the neural network. That's just using the coarse level. What we're seeing really is that for this peaks problem, the problem is basically solved at the point where we switch from the coarse neural network to the kind of medium level neural network. And so for the Indian pines, you actually see a steady improvement in the accuracy in a commensurate kind of change in improvement performance. So the point here is that nested iteration is going to yield a better validation accuracy in less time. So the other thing that we think is interesting is that by doing this regularization approach, we're pushing the parameters, by doing this nested iteration approach, we're pushing the parameters to different kind of regimes of the parameter space. Okay, so if you just train a fine level neural network, there's no notion of continuity between the weights and the biases from one layer to the next. And so what we did is we wanted to kind of explore whether this was leading to some sort of implicit regularization. And so we took 4 different hyperparameters, so Tikhonov regularization and the initial weights that we use in the matrix, the scaling of the randomization. And we did 12 independent runs for each hyperparameterization, so 48 total runs. And we looked at the 5-channel peaks and the 8-channel peaks, and we looked at the variation of nested versus non-nested. So if you look at this, the maximum for the nested is a little bit higher than the non-nested. But the interesting thing is the range over the median and the min, or the maximum and the min for the of sampled studies is much smaller, smaller than the non-nested. So we believe that this kind of is an interesting kind of data point. I wouldn't say it's definitive, that maybe this nested iteration is actually providing some implicit regularization, which can help improve the robustness of your neural network training. So the last thing I wanted to present is this torch braid library that we've just recently kind of released. We've kind of taken this layer parallel code, we've taken PyTorch and XBraid, and we've combined them together in a cool graphic. And so here I have to apologize for my lack of graphic skills, but that's the current icon I have. So we are now kind of released this torch braid library. It'd be interesting to find additional collaborators and helpers on this in this early stage. But it's built on this idea of using ODE networks and PyTorch instead. And so the architecture of this is pretty simple. We have XBraid talking through Cython, which is the C Python interface, with PyTorch and MPI for Pi for parallel communication. And we end up building what's called a module. That's the kind of building block of neural networks that use in PyTorch. And so what you can do is pass in basically a Lambda function for each network layer, and then a number of local steps, a parallel communicator, and a final time value. And this will build you a parallel neural network that's a layer parallel neural network that will have both forward and adjoint kind of derivative computation capabilities. And so that's built into using AutoGrad and all that stuff in PyTorch. Initial kind of forward propagation results show pretty promising. So we're looking at a 3x3 convolutional neural network with layers of 256 by 256. We've got steps here is just the number of layers. If you take each step has two convolutional layers. And so we're looking at just a forward propagation. We're seeing the performance increase. So in this case, this dashed purple line is the serial runtime that we get from PyTorch directly. And we see that we're basically getting a 10x speed up over this for forward propagation. We have similar results for back propagation. I just haven't made them yet into a nice plot. And so this is kind of showing two things. One is we get nice weak scaling as the problem size, or nice strong scaling as the problem size grows, but also weak scaling as we add layers, we only get mild drift in the runtime with each additional layer. So to close, I presented this layer parallel algorithm for training deep neural networks that Stephanie had kind of talked about earlier. I talked more about the nested iteration that's trying to overcome some of the challenges associated with initialization. I also presented the kind of first torch braid results with faster forward propagation. And so I'm pointing to a couple of papers here. This is this original paper, and then this is on the nested iteration. So with that, I'll close and take any questions. Thank you.
Thank you for the great talk, Eric. We'll have time for a quick question. Thank Eric. While Colin can set up his screen. Any questions from the audience? If not, I actually have a quick question. So for these multi-level schemes, parallel and time schemes, is the training very different from training the standard serial method? So like, do we have to change the hyperparameters very drastically?
I wouldn't say it's a whole lot different at this time. You still have to do kind of hyperparameter searches and scans. We're hoping that there is eventually some regularization that comes from the multi-level nature that provides a little more robustness, and that was kind of what I was getting at in those last slides. But I wouldn't say that it really kind of we've definitively kind of worked through that at this time to be able to make a concrete statement there.
Thank you. So we'll probably have more time to discuss after the whole mini-symposium. But in the meantime, I guess Lars can